Good morning, everyone. How are you today? Excuse me, can you hear me? Hello? Excuse me, do you hear me? Okay, thank you. So welcome to Fluid Mechanic. Okay, this one is week one of tutorial. So firstly, I want to introduce something about myself. My name is Đức Lượng Cao, and my information you can see in UTS Online. So UTS Online. UTS Online. Okay. Here's something. Okay, my name is Đức Lượng Cao, and my email address you can see in UTS Online. And if you have any question, you can ask me. Okay, my email here. And firstly, I want to say some very important information about this subject. In this one, you will have one quiz, 2 lab reports, and 1 project. And so that you have the final exam. Okay, and the quiz will be week 6. Here you will see lab 1 week 5, lab 2 week 8. Okay, and as you can see in the subject outline, the lab report will be 15%. Weight is 15%. Lab 2 15%. It means 2 lab 30%. Project 20%. Okay, and the quiz 20%. So the final exam just only 30%. Okay, so quiz, lab reports and projects are very important. All of them is 70% totally. Okay, the final exam just only 30%. So be careful. You have to study from now to the end of this semester. Okay, if you finish, everything is you have 70% pass, because that's only 50% you pass this subject. Okay, and one more thing about the tutorial. Okay, you have the document of tutorial here, tutorials. Okay, we have question from tutorial 0 to tutorial 11. However, we only have 9 tutorial, just only 9. But in the on the UTS Online we have 11. So some of them we not do it in the tutorial. You have to do it by yourself. Okay, and if you have any question, you can ask tutor or subject coordinator. It's up to you. Okay. Do you have any question about this subject? Do you have any question before we are coming to tutorial today? Any question? No? You don't have any question? Okay, you don't have any question. We will go to the first tutorial. In the first tutorial, here is tutorial 1. You have question and solution in here. Okay. And some question 1 is some example of fluid, example of application of fluid mechanics. I think this one, subject coordinator say about this one in the lecture already. Okay, you see we have so many applications of fluid mechanics. For example, you want to, at home, you want to pump water from the ground level to the higher level. You have to use a pump. And how to find the pump power? You apply fluid mechanics. Okay, in the body, the heart is a pump. It's pump blood to other parts of the body. So the heart is a application of fluid mechanics, and actually you have a project about the blood pump. Okay, if you have looked in the project is blood pump. Okay, and as I remember, this one you have to submit in week 9 or week 10. Okay, blood pump is very interesting. So fluid mechanics, there are so many applications of this one. Okay, and the textbook, I think the lecturer, this one, talk about this one already. Fluid mechanics, 7th edition. And this one you can borrow at the UTS library. Okay, or you can buy this one from, let me see, Wiley. Okay, so you can buy this one. Or in UTS online, you have course note. This one is very important too. It's a course note. Yeah, you see, this one free, and you can download and use this one in the quiz or final exam. Okay, this one is very important because at the end of the course note, you have table and figure. You have to use table and figures in the quiz and the final exam, and everything is online this semester. Okay. And this semester, as you know, you have 9 tutorial. Let me see, 4 face-to-face and 5 online classes. So it's up to you. You can attend to face-to-face if you in Sydney, or online you can attend to face-to-face, but recommend face-to-face because when you study face-to-face, you can ask the tutor as many as possible, or it's easier for you to understand everything. Okay, but for online class, if you have any question, you can ask me now or by email. Okay, the course note you can download in UTS online. Okay, do you have any question? Any question for me about the this subject, about the materials, anything? I will try to okay, some of you now. Okay, if you don't have any question, we will start with the first tutorial. Yeah, one question. We are not registered in a face-to-face class. Yeah, sure, you can. Sure, you can. You can attend to face-to-face or online. It's up to you. Okay, you register for face-to-face, but now you want to change to online. It's okay. You register for online. Now you want to change to face-to-face. Okay. Okay, it's up to you. Any question? No. Okay, so learning materials and tutorial. And now tutorial 1. Okay, this one. In the first tutorial, I will try to maybe summarize various fundamental knowledge of fluid mechanics, about fluid mechanic properties. Okay, some properties very familiar with you. It's very common, very popular, like pressure, temperature, or specific volume or density. Okay, but some properties maybe is the first time you hear about them, like Buck modulus of elasticity. Maybe viscosity is familiar with you, but lapse rate, boiling temperature, or something like that is a new property for you. Okay, so we focus on question 2 today. Okay, fluid mechanic properties, and I will have you how to find properties and where to find the properties of fluid mechanic substance. Okay, in the first question here, it asks you find the density of air in standard condition and water and seawater at 20 Celsius, mercury at 20 Celsius. Okay. It asks you find properties of air, water, and seawater. Okay, firstly, I open this one. Let me see. Okay. Firstly, you have to find density of air in standard condition. And in the standard condition. As I said, you in the UTS online, you have the cost note, okay, and you use cost note to find properties to find properties in fluid mechanics. Okay, this one is a cost note. You can download in UTS online. Okay, and in the first question, it asks you find property of air at the standard condition. Let me see. In the appendix, okay, if you have the cost note, you go to the appendix. And it may be table 8.1. Table 1, here is one. Okay, you find property of air in standard condition. Okay, this one is appendix of the cost note, and table 1 and 2. Okay, air is a standard condition. Yeah, you have the air density is 1.23. That's easy. Okay, the first tutorials have you how to find properties and where you can use table in the cost note, or you have textbooks, that's okay. Yeah, same. Okay, from monsoon here. Okay, from monsoon, this one is the textbook. So air in standard condition is 1.23 kilogram to meter cube. Okay. The first question, density of air in standard condition. And water and seawater at 20 Celsius. Water at 20 Celsius. Okay, table 1 and 2. US water and seawater at 15.6 and 15.6. Okay, and the next one here, you have the physical properties of water at other temperature. You see here, from 0 to 100 Celsius. You see the density of water. It does not change too much. It's at 0 is 999.8, 5 is 1000, 10 is 999.7, 15 999.1. Okay, so it's a normal condition. You can assume as the density of water is constant, is 1000. Okay, so in the quiz or the final exam, when you see water, density of water is 1000. Don't worry about 999.8 or 999.7. Okay, 1000 is accepted. So density of water, you can assume a constant 1000. Yeah, it's yeah, water at 20 Celsius, 1000. It's similar for seawater. You can assume as density of seawater is constant. Okay, it's constant. Yeah.
Can you show the air part as well?
Sorry, I can't hear you.
Show the air part again.
Air, density of air. Okay. Air. Here, air is a standard condition. You see, table 2, air standard.
Oh,
density, yeah, 1.23. Okay. So water, density of water is constant, 1000. Density of seawater is constant, and 1030. Okay. C, water, constant, water, constant. Okay, and mercury at 20. Mercury here at 20 is the 13600 kilogram per meter cube. Okay, the first one is just show you how to find properties of some substance in fluid mechanics. Okay, that's easy. Okay, do you have any question about this one? Use table only. Any question? No? Yeah, okay. No, okay. The second one, yeah. Vapor pressure of water. What is vapor pressure? What is vapor pressure? Vapor pressure, okay. So let me see. In fluid mechanics, you have two properties. It's vapor pressure and boiling temperature. Okay, for example, now you at sea level, you at sea level, and pressure at sea level is, do you remember it? Pressure is 101.3 kPa. Yeah, at sea level, pressure is 101.3 kPa. Now you are living in 101.3 kPa. Okay, and at this pressure, for example, you have a water tank, okay, and you heat it, and water will be boiled at 100 Celsius. Water boil at 100 Celsius. Yeah, this one is very common. When you go to the high mountain, okay, how about pressure? Do you know, how about pressure in the high mountain? This one is PO, this one is P1. How about P1? Higher or smaller than PO? Higher or smaller in the high mountain?
In the high mountains,
yeah,
water boils at a lower temperature. Is that correct?
Yeah, it's lower temperature. And how about pressure? P1.
Pressure is lower pressure at altitude.
Yeah, P1 will be smaller than P0. And at this pressure, water will be boiled at T1, smaller than TL. Okay. And in this case, we call that vapor pressure. Vapor pressure. Vapor pressure. Vapor pressure. PV at 100 Celsius is 101.3 kPa. And vapor pressure PV at temperature T1 is P1. This means if you want to boil water at temperature T1, you have to create a tank, and the pressure of water inside the tank is P1. Okay, it's vapor pressure. And similar, we have boiling temperature. Boiling temperature TB, okay, and TB at pressure 101.3 kPa is 100 Celsius, and TB at pressure P1 is T1. Okay, it means if you want to boil water at 100 Celsius, you have to create a pressure is 101.3 kPa. Okay, this one is vapor pressure and boiling temperature. Do you have any question about this one? No. So the question 2 asks you find the vapor pressure of water at 5, 20, 50, and 100 Celsius. Okay. At 100 Celsius, vapor pressure at 100 Celsius is 101.3 kPa. Okay, because if you want to boil water at 100 Celsius, you have to create a pressure. It's similar to ambient pressure now, it's 101.3. Okay, but 5, 20, 50, how to find vapor pressure? You have this table, yeah, use this table. Yeah, the table 3 is a first note. The first column you see temperature, and the last one is vapor pressure. Okay, so vapor pressure at the temperature 100 Celsius is 101.3 kPa. The question asks you at 5, let me see, at 5, 20, and 50, okay? 5, 20, at 5.87 kPa. It means if you create tank and pressure in the water, in that water tank is 0.87 kPa. Water inside the water tank will be boiled at just only 5 Celsius. Okay, just only 5 Celsius. At 20, you have here is 2.34 kPa. Okay, so water boil at 20 Celsius if the pressure is 2.34. 50, you have it 12.33. Okay, it's vapor pressure. Okay, do you have any question? Use this table. And there's question 2 about vapor pressure. And you have one question about boiling temperature. Yeah. Okay, boiling temperature. And we will work with this question later because this one is related to the attitude. Okay, and I will talk about attitude later. Do you have any question about this one? Use table. But you have to understand what is the vapor pressure and what is the boiling temperature. Okay, vapor pressure, yeah. And this one, if this one is pressure, this temperature is boiling temperature. Yeah. Question 3, viscosity of water at 5, 20, and 50. Viscosity will affect to the movement of an object in a fluid. For example, in the car, you have oil, and the viscosity of oil will be higher than water. Okay, so maybe if you when you choose oil for the car, you have to take care about the viscosity of the oil because it's different with a different kind of oil. Okay, and you have viscosity and kinematic viscosity. Okay, kinematic viscosity equal to viscosity over density. Okay, because density of water, density of the fluid is almost constant. So you have kinematic viscosity, viscosity over density. Okay, and how to find viscosity? Use table. In question 3, you have to find viscosity of water at 5, 20, and 50. Okay. Yeah, this table. Viscosity and kinematic viscosity. But remember that you see, viscosity times 10 power 3. Okay, this one is viscosity 10 times 10 power 3 equal to this value. Okay, so for example, you want to find viscosity of water at 5 Celsius. 5 Celsius. So viscosity of water at 5 Celsius will be equal to 1.518 times 10 minus 3. Okay, because viscosity times 10 power 3 equal to this one. Okay, so viscosity will be equal to this one times 10 minus 3. Yeah, it's similar for kinematic viscosity. Yeah, kinematic viscosity of water at 5 Celsius will be equal to 1.518 times 10 minus 6. Okay, be careful. Okay, because you see this one is viscosity times 10 power 3. Here is viscosity times 10 power 6. Okay, and because kinematic viscosity equal to viscosity divided by density. Okay, so density of water is 1000. So you see this one is 1000 times higher than kinematic viscosity.
But
Okay.
sir,
Yep.
I want to ask a quick question. That
Yep.
the viscosity,
Yep.
the line is mu times 10 to the power of 3. But
Yep.
why do you use in this one?
Okay, I will show you here. For example, at 5, okay. For example, at 5 Celsius, okay, viscosity times 10 power 3 equal to 1.518 is equal to 1.51 S. Okay, let me see. Let me check again. Yeah, Pascal second. Pascal second. So the viscosity will be equal to 1.518 times 10 minus 3. Okay, this one is viscosity. Okay, because you have viscosity times 10 power 3 will be equal to 1.51. Okay, 1.5 on it. Point. Okay, similar for 20 or 50 Celsius, and similar for kinematic viscosity. Okay, do you have any question? Yeah, kinematic viscosity is this question. Any question?
No.
No, okay. Question 4, surface tension coefficient of water. Surface tension, yeah. QS, a sample of question we could receive. Oh, question lab. Question lab. Which one?
Yes, please, sir. I think he means the question that we just did. I think he was asking if it's like an example of what we would receive in like tests and stuff.
Oh. Okay. I will talk about this one and that one later. Okay. Now we'll focus on this one first because we have to follow the schedule. Okay. We will talk about this one later as when you maybe at the end of this tutorial you can ask me again and I will talk with you.
Yeah, it's not the time, Jeremy.
Yeah. Surface tension coefficient of water at 5 and 60 Celsius. And what is for surface tension coefficient? Surface tension coefficient of water at 5 and 60 Celsius. Here you have surface tension. But what is surface tension? What is the surface tension? And here, for example, it's asks you find surface tensions of water at 560 Celsius. That's easy. Here, it's fine. You have surface tension here. At 60, you have surface tension here. That's easy. But what is surface tension? Okay. To understand about surface tension, we go to the last question. Yeah, this one. This one would be related to surface tension force and surface tension coefficient. Okay, the last one, this one. This one. Okay, read this one first. We have this question. Yeah. You have a maximum diameter of 5 centimeter long circular cylindrical steel needle with density is 8,000 kilograms per meter cube. That can stay afloat on the water surface at 20 Celsius. Okay. And similarly for a 10 centimeter long needle. You have this question, you have a needle. Okay, and then stay afloat on water surface. And why this one is stay afloat on water surface? How many force apply to this one? How many force apply to this one? Yes, I record everything and will upload in UTS Online. Okay, I record everything. Okay, how many force apply to this needle? How many force? When you have a needle afloat on water surface, how many force apply to this one?
2 force.
Yeah. How many forces? Weight of the needle. And this one afloat, it means we have to have an upward force. An upward force, this one is tension force. Tension force, and this one will relate to surface tension coefficient. Surface tension force, T, okay? And this one afloat on water surface, it means T will be equal to weight of the needle. Weight of the needle. Yeah. And this needle, you have the diameter D, the maximum diameter of you have to find D, and the length L is 5 centimeter long. Okay, it's 5 centimeter. 5 centimeter, or this one is 0.05 meter. Remember that in fluid mechanics, you have to change to SI unit. And as SI unit of the length is meter, not centimeter. Okay. And you have the density of the needle is 8,000 kilogram per meter cube. Okay. So this needle afloat on water surface if you have tension force, surface tension force equal to the weight of the needle. Okay. Something wrong here. Okay. Sorry, something wrong with my system. Okay. Weight of the needle. How to find the weight of the needle? Weight will be equal to mass mg. Okay, and m equal to density v z. Okay, it's weight of the needle. And equal to density v. The volume of the needle will be equal to P d power to over 4 times L times Z. This one is the width of the needle. Yeah. And the surface tension force. Okay, now, do you remember how to find surface tension force? T. Surface tension force will be equal to surface tension coefficient times the contact length between the needle and the water surface. The contact length, it means when you see from the top view, okay, you see here, the eye here, you see from the top view, okay, the contact between the needle and the water surface will be is this one, which this one is L, okay, and D, the contact between the needle and the water surface, okay, and the surface tension force will be equal to surface tension coefficient. Surface tension coefficient times the contact length between the needle and the water surface. Contact length is mean this one, L times D times, L plus D plus L plus D. Okay, so this one will be equal to 2D plus 2L. The contact length between the needle and the water surface. So from here, because this one is of course on water surface, so width equal to tension force or rho P d square root 4 times L times Z will be equal to surface tension coefficient 2D 2L. Okay. And the density is given is 8,000 kilogram meter cube. 8,000 okay. Length is 0.05 meter. Okay. So this one is Z. And Z, this one is 9.81. Okay. Length is 0.05 meter. Surface tension coefficient. Surface tension coefficient will depends on the temperature. In this case, water temperature. Okay. And you have water temperature is 20 Celsius. So we use the table at 20 Celsius. We have surface tension coefficient here is 0.0728. This one is 0.0728. Okay, so from this equation, you can find, sorry, not this one. It's then D. Yeah, surface tension coefficient is 0.0728. Okay, so from this equation, you can find D. D is maximum diameter of the circular needle. Okay, the maximum diameter of the needle to this one can float on water surface if the length is 5 centimeter. Okay, based on this equation, just only D you don't know, so easy to find D, and the result you can see in your test online. Okay, so this is surface tension coefficient you can find from the table. Okay, and from surface tension coefficient you can find surface tension force. Okay, surface tension force equal to surface tension coefficient times the contact length between the object and the water surface. Object and water surface. Okay, for example, you have this. I think in the online we have a video about this one. I show you. Maybe I think we have a video about this one. Not this one. No, don't remember. Learning material.
Sir, you froze. Are you still there?
RIP. I miss him already.
Oh, I'm the host. All right, cool.
Where's Duck gone? I miss him. He's my boy. Wait, Will, can you make me host?
All right.
Can you do that?
I can make you co-host.
Ooh, yes, please.
Put on some music while we wait.
Share the power.
Ooh. Mm. This does give you a lot of power.
I like how none of the Zooms have the permission set, so you can just give co-host to everybody.
Carter, teach us something.
All right. Right, boys and girls.
Actually, I have a question if anyone can answer it. The surface tension of the water, is that based on the perimeter? Like, I tried to ask it, but then he froze. Did anyone get that? The surface tension of the water for the needle?
I've got no
What?
clue.
I think it has to do with the temperature of the water.
It's the perimeter, not. But on one side of the
No.
equation, he had like the density of the needle and the volume of the needle, and then gravity. And then on the other side, it looked like he had the perimeter of like the rectangle that would have been the area of the water.
That one is
What
usually
he's saying is
calculated.
that the surface tension is
Tension.
equal to the internal pressure. So on one side, the surface tension was equal to like the surface area, which included, yada, 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 and then the coefficient of surface tension.
Mm-hmm.
Yeah. So it's
Degree,
basically like,
area or the millimeter.
so it's like what part of the cylinder comes in
Yeah, so you can take a look.
in the air.
Yes. Okay, thank you. I get you guys now. Sweet. See, we're learning.
Let's keep going.
Yeah, I
Go
know.
through questions without
Who's
him.
got the questions? Someone pop it up. Share your screen. We'll teach ourselves. Fuck it.
Yeah, anyone got the
This
question?
is recorded. This is actually going to go into the UTS online.
They probably won't. They normally do like one tutorial, so they'll choose a tutorial that isn't, not properly recorded. Or
I
do they
don't
record
think
every
it'll
single
ever
one?
be the one that's on 8 a.m. on a Wednesday.
Trim the video and edit this out.
Guess we'll just have to wait until he comes back.
If he comes back. Oh, yeah, okay, the back.
Is he?
I see his face cam.
Yeah, it says big man's back.
Sorry.
Beautiful. Hello.
Oh, I'm so sorry.
Hello.
The internet connection at my home is too bad. I'm so sorry. And
It's all good, sir. No worries.
okay.
Yeah.
Yeah, so sorry. Okay, so we continue with UTS online. Go to UTS online again. So sorry. Fluid mechanic. And we finished surface tension coefficient. Let's see. Tutorial. Okay, so surface tension coefficient, and this one you have in from the table. Okay, and the surface tension coefficient you will use to find surface tension force. Okay, and surface tension force, how to find surface tension force you have from the last question. Surface tension force will be equal to surface tension coefficient times the contact length between the objects and the water surface. Okay. Buck modulus of elasticity of water at 20 Celsius, question 5. This one is, I think this one is a new properties, okay? And Buck modulus of elasticity of water. And this one, you have equation here. Buck modulus of elasticity E will be equal to minus delta P. Delta P is pressure change divided by delta V over V. Delta V is volume change. Okay, so this one is equation of elasticity. It shows the relationship between pressure change and volume change. Okay, and the Buck modulus of elasticity, this one you have from the table, is a cos note. Yeah, it's one. Yeah, this table. Yeah, the modulus of elasticity. Yeah, this one. Remember that E times 10 minus 6 equal to this value. For example, at 5 Celsius, E times 10 minus 6 equal to 2.05. So elasticity will be equal to 2.05 times 10 power 6. Okay, be careful. Elasticity, yeah. Surface Buck modulus of elasticity of water at 20 Celsius you have on the table. Then pressure required to reduce volume of water by 1%. You have to find the pressure required to reduce the volume of water by 1%. Okay. Yeah, I opens my iPad. Okay. Okay, in this question, you have to find, let me see again. You have to find the pressure required to reduce the volume of water by 1%. The volume reduce 1%, it means delta V volume change equal to minus 1%. You have to find pressure. I add the D into the equation and they do not equal X1. Yeah. Okay, the previous question, you asked me about the previous question. This one. Yeah. You see, in the solution, you don't have D. We will have a look at the solution in the UTS online. I know. Thank you for see the solution. You see, yeah. 2 times the surface tension coefficient times L equal to P. In the right hand side, you see, is the width of the needle, and in the left hand side is surface tension force. But in here you don't have D because D, the diameter, it usually is very small compared with L. D, very small compared with L. So in the solution, the subcoordinate ignore D in the equation. But actually, we can add D in here. It's, you see, D, if you see the result, D is just only 1.54 millimeter compared with 5 centimeter of the length. So D very small compared to L. So in the solution, subject coordinator ignore D in the is a solution. Okay. Okay. So it's up to you. You can have D in the equation, or you ignore D. It's up to you. But the result is almost the same. 1.54 or 1.53 or 1.55 is okay. In the fluid mechanics, the difference is smaller than 5%. It's very good. Smaller than 10% is accepted. Okay. Do you have any question? Any question? Hand is okay? Okay. So now come back to our question, this one. This question asks you about pressure and you want to reduce the volume of water 1%. Reduce 1% is mean delta V is minus 1%. Okay. And as I says, you have equation to find elasticity E equal to delta P over minus delta V over V. Okay, sorry, delta V over V is 1%, minus 1%. You can change 1%. Delta V over V is minus 1%. Okay, and elasticity of water at let me see, 20 Celsius. Elasticity of water at 20 Celsius. Here is 2.17 10 minus 6. Okay. So elasticity will be equal to 2.17 10 power 6. And this one is equal to 2.17 times 10 power 6. Okay. So from here you have delta P will be equal to minus delta V over V, it will be equal to 1%. It's 1% times 2.17 times 10 power 6, or this one is 21.7 kPa. Sorry, MPa, because this one is MPa. 20. MPa, megapascal. It means if you want to change 1% of volume, you have to use, or you have to change the pressure is 21.7 megapascal. It's very high pressure. Okay, so it means it's very difficult to change 1% of water, volume of water. Okay, you have to use 21.7 megapascal to change 1%. Okay, it's how to use elasticity. It's a properties of in fluid mechanics. It shows the relationship between pressure change and volume change. Yeah, elasticity. Can you see in the table? In the table here. Let me see. In the table, you see in the table at 20 Celsius. Okay, you have elasticity times 10 minus 6 equal to 2.17. Okay, you have this one from the table. This one is mean E times 10 minus 6 equal to 2.17. Okay, or elasticity will be equal to 2.17 times 10 6 power 6. Okay, be careful about this one. Okay, Book modulus of elasticity. Okay, do you have any question about this one? Kinematic viscosity is viscosity over density. This one is easy. Okay, we talked about this one already. Gas constant R of air, a standard condition. Gas constant. Do you remember this one? Do you remember this one? Gas constant. Gas constant. Do you remember ideal gas equation? Ideal gas equation. Ideal gas equation. Ideal gas equation. Ideal gas equation. Do you remember this one? Pressure equal to rho R T. Which pressure is this one? P is pressure. Rho is the density. T is temperature. But remember that temperature in Kelvin scale. In Kelvin. Okay, in Kelvin, not Celsius. And R here is gas constant. And gas constant. And gas constant you can find from table. Let's show you the table. The table. Gas constant, yeah. Air. For air, the gas constant is 286.9. Okay, 286.9. Okay, with a different gas, you have the different gas constant. For example, with carbon dioxide, you have gas constant is 188.9. Okay, for helium, you have 2077. Okay, with a different gas, you have the different gas constant. Gas constant you will use in the ideal gas equation. Yeah, and the gas constant you have from the table. Okay, that remind you some fundamental knowledge of fluid mechanics. Gas constant. Okay, pressure and temperature and density of ambient air in U.S. standard atmosphere at sea level at altitude of 1,000, 2,000, 5,000, 10,000 meter. Okay, in this question, you have to find pressure, temperature, and density at sea level and the higher level of altitude. Okay, see this one. How to find this one? Use table. Is this table? Oh, no, not this one. Here. The US standard atmosphere. In the left-hand side, the first column is altitude. Okay, temperature, absolute pressure, specific width, density, and viscosity. Remember that this one is absolute pressure. Okay, absolute pressure. In fluid mechanics, you have 3 pressure. You usually work with 3 pressure: ambient pressure, absolute pressure, and gauge pressure. Okay, gauge pressure. You have usually 3 pressure. Let me say so. Ambient pressure, P ambient, absolute pressure, absolute pressure, P absolute, and gauge pressure. Okay, ambient pressure is very familiar with you. Ambient pressure is the pressure of ambient is 101.3. Okay, absolute pressure is actual pressure, and gauge pressure will be equal to is the pressure difference between absolute and ambient. Okay, for example, you have a tank, and pressure inside this tank is for example, 120 kPa inside the tank, and the ambient pressure is 101.3 kPa. Atmospheric pressure is 101.3 kPa. In this case, you will have P ambient is 101.3, P absolute is 120, and P gauge pressure is 120 minus 101.3. Okay, it's gauge pressure, so use pressure different between absolute pressure and ambient pressure. And the pressure you see, yeah. Do you have a question? You have, excuse me. Remy, you haven't, you raise a hand? No? Okay. So gauge pressure, so use pressure difference between absolute and ambient pressure. Okay. And the pressure you see in the table is absolute pressure. Okay. But the pressure, maybe pressure you see in measurement is gauge pressure. In the measurement is gauge pressure. But pressure in the table, in the textbook, in the course note is absolute pressure. Okay, so be careful. If you have gauge pressure, you have to change to absolute pressure in the calculation. Okay. So in this question, it's asks you find pressure, temperature, and density at sea level and altitude 1,000, 2,000, 5,000, 10,000. Use the table. What's the problem with the table? Sorry, something wrong here. I'm going to use table here. Can you see the table? The question asks you find the the pressure, temperature, and density in the US standard atmosphere at sea level, altitude 1,000, 2,000, 5,000, and 10,000 meter. Okay, so here's the table. Altitude 0 is mean sea level. You have temperature, you have pressure, and you have density. 2,000 is okay. 10,000 is okay, but 5,000. How to find the temperature, pressure, and the density at 5,000 meter altitude when you don't have 5,000 in the table? How to find? How
Can
to
you take the average of 6,000 and 4,000?
Yeah. Interpolate. Okay, so in this case, you have at the altitude 4 kilometer and 6 kilometer. Okay, and have temperature T1 at 4 kilometer. You have temperature T2 at 6 kilometer, and you have to find at 5 kilometer temperature T at 5 kilometer. So you have the equation 5 minus 4 over 6 minus 4 will be equal to T minus T1 over T2 minus T1. Okay, interpolate. It's similar for if you don't have any values in the table, you have to use interpolate. For example, you want to find a temperature and pressure at 4.2 kilometer. Use interpolate. 4.7 interpolate between 4 and 6. Okay, this one interpolates. You have to use this one so many times in fluid mechanics because in the table it's only show you some value, not everything. Okay. So pressure, temperature, and density you have from the table. And sometimes you have to use interpolate to find the value. For example, at 5,000 meter. Okay. And check the ideal equation P equal to rho RT. Because R is constant already. P you have from the table, density you have from the table, and temperature you have from the table. And you can check the ideal equation. Sure that is correct. Okay. Try to do it by yourself. The lapse rate B. Lapse rate B. B equal to change in temperature divided by corresponding change in altitude. And this one is easy because temperature and the altitude you have from the table. For example, from the table here, okay, you want to find the lapse rate between 4 and 6 kilometer. Okay, you use change temperature minus 11 minus 23.96 divided by 2. You will have the lapse rate. Lapse rate equal to change in temperature divided by corresponding change in altitude. Okay, and the lapse rate B 6.5 Celsius per kilometer. Mean when you go up 1 kilometer, the temperature will be decreased 6.5 Celsius. Okay, go up 1 kilometer, temperature decrease 6.5 Celsius. It's a lapse rate B. Okay, you have equation here. 1 kilometer in you go up 1 kilometer, temperature decrease 1 Celsius. Boiling temperature of water. Okay, I said about boiling temperature already. For example, boiling temperature at 101.3 kilopascal is 100 Celsius. And in this one, you have to find the boiling temperature of water at 8,000 meter altitude. Okay. you find the boiling temperature TB at 8,000 meter. Boiling temperature. Okay, we go back to this one, this table. Boiling temperature is the first one, and vapor pressure is the last one. It means we can find boiling temperature if we know pressure. Yeah, if we know pressure. So to find the boiling temperature, we have to find pressure at 8,000 meter. We have to know pressure at 8,000 meter. Okay. If we know pressure, we use table to find temperature. Okay. And pressure at 8,000 meter is the previous question. Pressure at 8,000 meter altitude. Next one here, 8,000 meter altitude here. So absolute pressure is 35.65 kPa. 35.65. So you have pressure at 8,000 meter is 35.65 kPa. Okay, it means when you go up to 8,000 meter, the pressure is just only 35.65 kPa. And when you have pressure is 35.65 vapor pressure, 35.65 it means between 31.16 and 47.34. Okay, so the boiling temperature is between 70 and 80 Celsius. Now use interpolate. Okay, interpolate. We have the table here. So we have at 70, table at 70 Celsius, you have this one, the temperature, this one, the boiling PV vapor pressure, and vapor pressure at 70 is 31.16, 31.16, okay, at 80 Celsius is 47.34, okay, and you have to find temperature T at pressure 35.65. Okay, you have to find temperature at 35.65. So you will have T minus 70 over 80 minus 70 will be equal to 35.65 minus 31.16 over 47.34 minus 31.16. So from here you have boiling temperature at 8,000 meter altitude. Okay, that's easy to find temperature from the equation. Okay, and the result you have in here is 72.8 Celsius. 72.8. Okay, it means at 8,000 meter altitude, water boil at only 72.8 Celsius. Okay, this boiling temperature. Do you have any question about this one? Any question? No? Okay.
Yeah, sorry, where did you find the 70 and 80 degrees? In which table were they?
Yeah. '70, you see at 70, pressure is vapor pressure is 31.16. Okay. At 80, pressure is 47.34. Okay. And our pressure is 35.65 between 31 and 47. Okay.
All right.
So the temperature between 70 and 80.
All right, thank you.
Yeah.
Sorry, how did
Yep.
we find the vapor pressure that we're looking for?
Vapor pressure, as I said here, at the beginning, not this one. Yeah, vapor pressure. As I said, vapor pressure at 100 Celsius is 101.3 is ambient pressure. Okay, and when we go up, temperature decrease and pressure decrease. Okay, and vapor pressure is mean if you want to boil water at temperature T1, you have to create a vapor pressure P1 for water. Okay, it's similar for boiling temperature. And in the the table here, if the first column is the temperature, the last column will be its vapor pressure. And if the last column here is the pressure, the first one will be is boiling temperature. Okay, first and the last. First is the temperature. For example, temperature of water you have to find vapor pressure is the last one. Okay, if you have water at this pressure and you want to find boiling temperature is the first column. Okay, first and last. Any question?
No, that's it. Thank you.
Yeah. So next one is sound speed. Sound speed in the air and sound speed in the seawater. Sound speed in the air, I think this one you have equation already. Yeah, sound speed in the air, A equal to KRT power 1/2. With T temperature, I is gas constant from this table. K is constant from the table. Specific heat, constant specific heat, K and K here. Specific heat ratio, K. For air, K is 1.4. Okay, R is 2.869. So K and R constant. So sound speed will be depends on temperature. Okay, depends on temperature. So in this question, you have to find the sound speed at sea level and 8,500 meter altitude. When you go up, temperature decrease. So the sound speed at 8,500 meter altitude will be smaller than sound speed at the sea level. Okay, and the results in the solution is incorrect. You know why it's incorrect? This one is no. I will ask the coordinator change this one. It's incorrect because at 8,500 meter altitude, the temperature not 40.2 Celsius at 8,500 meter. Yeah, and you can try to find it by yourself. Okay, this 8,500 is minus 42 Celsius, not 42. Not positive, it's negative. Okay, that's why, yeah, this one will be is minus 40.2 Celsius. So the sound speed will be smaller than sound speed at the sea
Sorry,
level.
the table says minus 36.
Minus.
Oh, 8.5? Okay.
Yeah, 8.5. It's minus 40.2. Okay, so you can find the sound speed by yourself. It's smaller than 340 meters per second at the sea level. Okay, subspeed in the air, and sound speed in the seawater. We can use this equation for sound speed in the seawater because seawater is not gas. Seawater is a liquid. Okay, remember that R is ideal. R and K is for ideal gas. For gas, so we can use this equation to find the sound speed in the seawater or in the water. Okay, and we have another equation to find sound speed in the liquid, equal to elasticity divided by density. Okay, this one. Okay, this one is equation to find sound speed in the seawater or in the water, in the liquid. Okay, with elasticity you have from the table, density from the table. Okay, and you have sound speed in the seawater is much more than sound speed in the air. 1,500 meters per second, maybe 4 or 5 times higher than in the air. Okay. So remember that in the air, you use this equation. In the seawater, you use this equation. Okay. Do you have any question about sound speed? No? Okay, so we finished the question 2. Okay, Smith question 2. This one is surface tension coefficient or surface tension force. We did it already. We finished the question 2. Okay. From this semester, a tutorial just only 1 hour and 30 minutes, not 2 hours as previous semester. So we stopped now. And if you have any question, you can ask me. Actually, we still have one more question. Is question 3 here? Question 3. Question 3. Yeah. Okay. And we will finish this one later. What temperature is? Okay. Okay. Yeah. You see, at 8,500 meter altitude, the temperature, as I said, is minus 40.2, not 40.2, because here you see the altitude 8 kilometer, minus 36.94, altitude 10 kilometer, minus 49.90, and you use interpolate to find the temperature at altitude 8.5 kilometer is minus 40.2 Celsius, minus 40.2 Celsius, not positive. This one is negative. Okay, so you will have the different sound speed here, smaller than 340 meters per second. Okay, any question? Okay, if you don't have any question, thank you. And if you have any question, you can email me. My email you can find in if there's online. I'm so sorry about the internet connection today. Okay.
Thank you.
Yeah, thank you.
Thanks.
Thank you very much.
Yeah, thank you. Bye-bye.
Thank you.